Hey guys, welcome back. So today we're going to talk about when a function is differentiable and when it isn't, and where it is differentiable and where it isn't. And differentiable is just a fancy word that means you can get the derivative there, okay? So if you can get the derivative, it's differentiable. So I'm going to start with just a graphic approach. In order for it to be differentiable, in order for us to be able to get a derivative, the function has to be continuous and smooth, okay? So if you look at these examples, there are 4 cases where the derivative doesn't exist, okay? Basically, for this graph, the absolute value graph, the derivative does exist everywhere here. And remember, it's just the slope of the curve. Well, that's a straight line, so it has a numeric slope. It actually has a slope of 1. Over here on the left side, this is still a straight line. The derivative exists everywhere there as well. But at the sharp point right here, the derivative does not exist right at that sharp point, okay? And the reason is the left-hand derivative and the right-hand derivative are not the same. It's not a smooth corner. It's a sharp turn, okay? So that example, a sharp point, can look like a corner. I don't really care what you call it, a sharp point. They can also call it a cusp. This one's called a cusp. But to me, these two look like the same thing. The derivative exists everywhere except at that sharp point, okay? So, and you can just say sharp point. Now, the technical reason is left-hand derivative doesn't equal the right-hand derivative at that sharp point. Another place the derivative will fail to exist is if there's a vertical tangent. I find this one a little bit more difficult to see, though. So right here, there's a vertical tangent. If you visualize a parabola, we know the slope here is 0. Well, if you turn that parabola sideways, this would have a vertical tangent. So there, the slope would be undefined. Well, that's the same thing that's happening in this graph, but this one is a function. This one's not. So there's a vertical tangent right here because that curve is like half of a parabola and then flipped to half of a parabola. So vertical tangent is the other place. That one's a little harder to visualize. And lastly, and most commonly, it's not going to be differentiable if it's not continuous, okay? It must be continuous in order to be differentiable. So to summarize everything you see here, it's not differentiable at a sharp point, okay, that's these two. It's not differentiable at a vertical tangent, right there. And it's not differentiable if it's not continuous, and that's a big one. Okay, so using just that simple, easy explanation, where would the derivative fail to exist on these graphs? Well, at x equals 1, sharp point, derivative fails to exist. At x equals 2, derivative fails to exist. At whatever this point right here is, derivative fails to exist because it's discontinuous. And also at this spot right here, sharp point. On the other graph, the derivative does not exist there at 0. And the derivative does not exist here at 3 because it is discontinuous, okay? So it has to be smooth and curvy. Okay, so now if you know what this graph looks like, then you can answer this question in a heartbeat, okay? This would be very easy if you know that this is the absolute value graph and is shifted to the right 5 units. If you know that, then you know it has a sharp point at 5, in which case f of x is differentiable for all values of x except when x is 5. If you didn't know that, then it would be a little bit harder to figure this one out. And the way you would do it, believe it or not, is you have to turn these absolute value bars, turn that into a piecewise function of 2 pieces. This one function is actually the equivalent of 2 different ones. X minus 5 and the opposite of everything inside there, negative x plus 5. The right side of the graph is the graph of x minus 5 when x is greater than or equal to 5. The left side is actually the opposite when x is less than 5. So if you didn't know what the graph looked like, you would have to do all this work. Split it into 2 pieces, Then you would find the derivative of the two pieces. The derivative of this is 1. The derivative of this is -1. And there's no x to plug into, but normally you would have to plug in this point that they have in common. And you'd say the left-hand derivative does not equal the right-hand derivative, and that's why it's not differentiable. But all of this work is not needed if you just know that the absolute value graph looks like that. Okay, so a piecewise function. This is probably the most common way of seeing this differentiable question. So first, you have to remember, big stars all over your notes. To be differentiable, it must first be continuous. Okay, so to show it's continuous, remember you have to plug the 1 in to both pieces. Okay, and this is often a free response question, so you have to say that you considered it. It's continuous, okay, if those two pieces meet at the same value. So I plug in a 1 on the left side, and I'm going to get 1 minus 2 plus 2 for the left piece, and that's going to be 1. And on the right piece, I also get 1, so at least it meets the first prerequisite. It is continuous. Then you have to go on to the second part and show that it's differentiable at 1. To be differentiable, you're going to find the two derivatives and plug in the 1 also. So the derivative of this piece would be 3x squared minus 4x. The derivative of this piece would be 2x. They have to be equal at x equals 1. So now I'm going to plug in the 1 to both of them. The left side is -1 and the right side is 2. Clearly they're not the same, so this is not differentiable at 1. It was differentiable everywhere else except for that part where they meet. Since these two pieces did meet at the same spot, this would be a case of one graph meets the other graph, but they meet at a sharp point. That's why it's not differentiable, but it was continuous. Okay, so hopefully that wasn't too bad. Good luck.